Hi everyone, good evening. I'm Vidushi Sharma, a postdoc fellow at KTH. Firstly, I thank the organizers and COSPAR committee. Here in my presentation, I'm going to focus on spectro-polarimetry studies of GRBs. In last talk, Tanmay has given a fantastic talk over hard X-ray polarimetry with AstroSat. Now I will discuss about the prompt emission physics of GRBs using these observations. Beginning with a brief introduction of GRBs. When gamma ray burst happens, it outshines all other gamma ray sources in the sky. Here in the background, gamma ray sky as observed by Fermi telescope is shown. What we see immediately is gamma ray flashes, which originates close to the burst site and known as prompt phase. This happens only for a few seconds. The light curve of prompt emission of GRBs as observed by AstroSat are plotted here. These sources are hard to study due to their non-repetitive transient nature. Each GRB is unique, which varies in shape, number of peaks, and duration. Now moving on to the origin of these bursts. They are formed by mergers of compact objects such as neutron star mergers or core collapse of massive star. At the end, central engine is formed, which can be neutron star or black hole that accretes the surrounding matter. Initially, a dense, high temperature fireball is launched. Due to high radiation pressure, the fireball expands. At certain point, the photon decouples from the plasma and produces thermal emission at the photosphere. It is the deepest region of the GRB that can be observed. Later, the jet kinetic energy dissipates into optically thin region and produces non-thermal radiation via internal shocks within the jet. In this scenario, the fast-moving shell clashes into slow-moving shell and differential kinetic energy is dissipated. These heated electrons are cooled off by non-thermal radiation such as synchrotron or inverse Compton scattering. Thus, the observed spectrum is combination of both emissions, photospheric and non-thermal radiation. This composes the entire prompt emission and is observed in gamma ray band. But the emission doesn't end here. The jet further crashes into ambient medium via external shock. The emission observed during this phase is known as afterglow emission. These radiations are observed in entire electromagnetic spectrum ranging from radio to gamma ray sky, and they are observed in days to month long time scale. The nature of the observed prompt emission is still an open question. The key outstanding questions in this regard are understanding the radiation mechanism, whether coming from photosphere or non-thermal emission, what is the dynamic of outflows and how it evolves with time, and what is the composition of these jets, whether they are period dominated or Poynting flux dominated. So now let us understand this by probing the emission mechanism. So the underlying radiation is mostly studied by spectrum analysis. GRB spectra are traditionally described by a joint, smoothly broken power law function known as band model. It is characterized by three parameters: low energy spectral index alpha, E peak, and high energy spectral index beta, and is non-thermal in nature. In simplistic picture, alpha values are tested against theoretical predictions. Also, other empirical models as well as physical models are fitted to the data. Detection and studies of GRBs are done using many observatories. One such mission is AstroSat, which has observed more than 500 GRBs. In our work, We explored cadmium zinc telluride imager onboard AstroSat at some MeV spectroscope, and the main findings were fluxes obtained from CZTI spectral fitting were consistent with Fermi, and in the absence of Fermi observations, CZTI along with BAT is capable of providing constrained parameters. Now, moving on to the limitation of spectrum analysis. Currently, it is observed that the same data, when fitted with different spectral models, can provide equally good statistics as demonstrated here. For example, same GRP present similar fit statistics for band and synchrotron model. This leads to degeneracy among the models. Therefore, there is a dire need of additional constraining observable like polarization. Now, I will talk about a little bit how polarization can play a vital role for unveiling the emission mechanism, starting with synchrotron emission produced in an ordered magnetic field scenario. Here, face-on view of GRB jet is shown, where theta j is jet opening angle, 1 by gamma is observer's cone. As magnetic fields are ordered in theta direction, the perpendicular polarization vectors are ordered in radial direction. This results in high polarization fraction when jet is viewed within the jet cone, but polarization fraction drops as one moves away from the jet edge. Now, for the random magnetic field scenario, the polarization vectors are randomly oriented. Therefore, they cancel out and produce null polarization fraction when jet is viewed within the jet cone, whereas at the jet edge and beyond, there exist some polarization vectors which are not equally cancelled out and thus produce net polarization fraction at jet edge. Another possible radiation mechanism is inverse Compton scattering. Here, polarization fraction versus jet geometry is shown in below plot. There, blue curve presents Compton drag model. Green line presents Q equal to 1, represents when jet is viewed at the edge. For Q less than 1, presents when jet is viewed by on-axis observer. For the scattering process, as polarization vectors are randomly oriented, results in negligible polarization fraction within the jet cone, whereas at the jet edge and beyond, some of the polarization vectors are not cancelled out due to asymmetry in the viewing cone and thus presents high polarization fraction beyond the jet edge. So now the polarization measurements in astronomy is a hot topic and quite challenging for transient events. The CZTI onboard AstroSat is actively measuring the polarization in hard X-rays. Briefly discussing the AstroSat CZTI as hard X-ray polarimeter. In hard X-ray, the dominant means of interaction between photon and detector is Compton scattering. The Compton scattering cross-section can be written as cosine function form, where A, B, and phi are related to polarization fraction and polarization angle. Eta presents the azimuthal angle. This azimuthal angle distribution of Compton scattered photon is measured. CZTI is a pixelated detector as shown on the left. An incident photon interacts with one of the pixel and it gets Compton scattered to nearby pixel. For unpolarized beam, all nearby pixels will register equal number of Compton counts. Hence, azimuthal distribution will form almost a straight line as shown in red, whereas in case of polarized beam, The electric fields have preferential direction to some of the angles and more photons are registered there. Therefore, it forms a cosine modulation curve, which is shown in black curve. So recently, this week, our in time integrated polarization catalog paper is accepted. There we have reported the polarization of 20 GRBs in 5 years of AstroSat observation, as already discussed in Tanmay's presentation. Here, polarization fraction versus E peak for each GRB is plotted. The majority of GRBs are found to possess low or null polarization and shown as upper limit. Interestingly, we obtained well-constrained polarization for 5 GRBs in this work. So at this stage, the current constraint sample is not enough for obtaining the generic radiation mechanism in GRBs through correlation studies, and we expect in future observation. For some of the key observations, the time resolved spectro-polarimetry has been carried out by AstroSat team, and these GRBs are listed here. In these work, the emission mechanism is understood using the joint observation from AstroSat, Fermi, and Swift Observatory. Further in my presentation, I will discuss the time resolved spectropolarimetric analysis of two GRBs. Let us begin with first interesting case GRB 160821A. It is the third brightest burst observer for me and is observed in entire spectrum from KV to GV range. The polarization analysis was done using AstroSat data for the main episode. We found low modulation, hence low polarization fraction was observed. Then hardness ratio was estimated using Fermi data, and there we found a distinct change in hardness ratio from rise to peak, then peak to decay phase of the burst. Hence, we carried out a finer time resolved spectroscopy. There, interestingly, we notice a change in polarization angle twice, which is consistent with change in hardness ratio. Therefore, we divided the main episode in 3 coarser time bands for detailed polarization. Here, in the upper plot, modulation curve is shown in lower panel. Polarization fraction versus polarization angle contours are shown. As first interval indicates high polarization, it implies the existence of net polarization vector in the observing cone. Then we see again a high modulation for the second interval, which shift in the phase. Then again we observe in polarization angle from second to third interval. This twice change in polarization angle during single emission episode is the only observation to date. The key observation results as follow. From the spectroscopy, we find degeneracy among various models. The spectropolarimetry results are well constraining the emission mechanism and as following. As this was the third brightest GRB observed by Fermi, which suppose the fact GRB is viewed by on-axis observer, burst showed broad spectrum with multiple peaks. Here, expected polarization fraction versus jet geometry is shown for synchrotron ordered, synchrotron random, and Compton drag model. As jet viewed by on-axis observer, the pink is the region of observation. There, synchrotron emission produced in ordered magnetic field can only explain the observed high polarization fraction. Knowing it's a synchrotron emission from the spectropolarimetry, we have tested the data with synchrotron model. Since it was a bright burst, a fast cooling synchrotron was used for all three polarized intervals. Here, electron distribution and synchrotron fit spectra are shown For the first and third interval, as presented in blue and green, Maxwell equivalent electron distribution is considered. For the third interval, in orange color, the main finding is appearance of extra power law, which indicates the onset of particle acceleration. Here, evolution of outflow parameters are shown on the right side, where we observe change in electron distribution during the burst. So now, moving on to spectro-polarimetric study of another interesting GRB, and here like of GRB 160325 is shown. It consists of two distinct emission episodes and is observed in wide energy range. Interestingly, this GRB is observed on access to CZTI instrument. Only such observation so far. For the spectrum, we observe first episode is best fitted with blackbody and cutoff, and second is fitted with cutoff power law model only. From polarization analysis, here Compton light curve is shown for CZTI. The first episode is found to possess low polarization fraction, thus we have reported our upper limit as 37%, whereas second episode exhibits high polarization fraction and we have reported greater than 43 polarization fraction as shown in high modulation curve. Here, I will discuss the physical picture obtained for this burst. We observe transition in the spectrum, we observe transition in polarization, and the temporal evolution of afterglow indicates that is viewed by on-axis observer. Thus, using composite modeling from polarization spectrum and afterglow allows us to infer that outflow is barium dominated with mild magnetization, where the first episode is coming from the photosphere where kinetic energy is getting dissipated below the photosphere and produces energetic electrons. These energetic electrons upscatter the upcoming thermal radiation and produces quasi-quantized thermal spectrum. In the spectrum process, the polarization vectors are randomly oriented for on-axis observer. Hence, inverse Compton, we observe low polarization fraction for on-axis observer. For the second episode, which is generated above the photosphere in optically thin region, the emission is produced by a synchrotron in ordered magnetic field, and thus we observe high polarization fraction for a jet viewed by on-axis observer. Finally, the conclusion is from time-integrated polarization, results so far, most of the bursts are unpolarized. They are either intrinsically unpolarized due to radiation process or there is a hidden change in polarization angle. This can be investigated using time reserve analysis of bright GRBs. For example, the first pulse of GRB 160325A was found to intrinsically unpolarized, and for GRB 160121A, the time resolved analysis indicates the change in polarization angle. Therefore, the spectropolarimetric studies are instrumental in pinpointing the emission mechanism. Once the mechanism is known, the detailed dynamics of emission regions can be studied. Thus, we look forward for much more well-constraining observations for obtaining the generic picture of the radiation mechanism. And thank you for listening.